Everyone is asking who will win the race for optical interconnects in co-packaged optics. Is it Ayar Labs, Lightmatter, Ranovis, or someone else entirely? The stakes are not just about bandwidth density or raw silicon speed. The real problem is that the entire industry is betting on a solution that fails the moment you try to cool it. By the end of this explanation, you will understand why the winner of this race will not be the company with the fastest chip, but the one that solves the mechanical engineering of thermal expansion and sub-micron alignment. The narrative in the robotics and data center communities is dominated by the promise of optical interconnects. We are told that moving from copper to light will slash energy consumption from 600 femtojoules per bit down to the 1 to 10 femtojoule domain. This is a staggering theoretical improvement. It suggests a future where data centers consume a fraction of their current power while delivering 10 terabytes per second per square millimeter. These numbers come from academic papers and industry roadmaps. They paint a picture of a revolution driven by photonics. But there is a critical gap between the simulation and the physical reality of a high-power AI training cluster. Here is the thing. The race is not being won on the silicon wafer. It is being lost in the packaging. When you look at the leading startups like Ayar Labs and Lightmatter, you see them pushing hybrid electro-optical architectures. They are demonstrating impressive modulation speeds. They are proving that silicon photonics can carry data, but they are all facing the same invisible wall. That wall is the mechanical integration of dissimilar materials. You are trying to bond a silicon photonic chip to a silicon electronic die, and then attach a heat sink, all within a stack that must remain stable under extreme thermal loads. Consider the precision required. Co-packaged optics demand sub-micron alignment tolerances between the optical waveguides and the electronic components. In a traditional pluggable optical module, the alignment is static. Once the connector is plugged in, the distance between the fibers does not change. In a co-packaged optics system, the alignment is dynamic. The system heats up during heavy AI workloads. Different materials expand at different rates. The silicon expands, the ceramic substrate expands, the metal heat spreader expands. Because of this mismatch, the optical path drifts. A shift of a few hundred nanometers can break the connection entirely. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This is where the industry hits a hard ceiling. The primary failure mode in CPO deployment is not signal attenuation or bandwidth limits. It is mechanical stress induced during thermal cycling. Every time the system powers on and heats up, the materials strain. Over time, this causes permanent drift in the optical path. The light no longer hits the detector. The link fails. This is not a software bug you can patch. It is a fundamental physical constraint that requires hermetic packaging and active cooling infrastructure to solve. Now, consider the yield risks. To make this economically viable, the industry is looking toward wafer-scale photonic fabrication. This means building entire arrays of optical components on a single reticle. On paper, this offers massive scale. In practice, it introduces catastrophic yield risks. A single misaligned micro-lens or a thermal expansion mismatch can scrap an entire reticle. If you are producing chips at a rate of thousands per month and one defect ruins the whole batch, your cost per unit skyrockets. The entity that solves this yield problem will dominate the market. The one that does not will be left with expensive prototypes that cannot scale to mass production. The consensus among researchers is that the sensible push toward CPO is currently bottlenecked by packaging yield rather than optical performance. We have the theory, we have the prototypes, we have the simulation data showing potential bandwidth densities exceeding 10 terabytes per second per square millimeter, but these figures remain theoretical for mass production. The complexity of co-integrating dissimilar materials is the true barrier. The race has shifted from pure silicon speed metrics to solving what we call the interposer war. This interposer war is not about who can modulate light faster. It is about the mechanical integrity of the three-dimensional stack. It is about the ability to maintain optical coupling under thermal load. Companies are now pivoting their focus. They are no longer just optimizing the laser diodes or the modulators. They are designing active alignment feedback loops. They are engineering thermal expansion coefficient matching between the electronic die and the optical waveguides. They are building cooling systems that can integrate directly into the optical interposer without introducing vibration or thermal gradients that break the alignment. This is the decisive factor for commercial viability. NVIDIA and Google are already integrating optical interconnects in specific contexts like TPUs and future GPUs. They are using them where the thermal environment is controlled and the distances are short. But for the general-purpose high-performance computing clusters that will drive the next decade of artificial intelligence, the solution must be robust. The system must survive thousands of thermal cycles without drifting out of alignment. There is a significant knowledge gap remaining regarding long-term reliability data. We do not yet have the empirical failure modes for high-power AI training clusters running at full capacity for months on end. We are guessing at the lifespan of these optical paths. We are estimating the stress limits of the adhesives and the solder joints. Until these mechanical constraints are empirically resolved, the ultimate market leader remains undefined. It will not be the company with the flashiest silicon. It will be the company that treats the optical interconnect as a mechanical system first and a communication system second. The engineering challenge is to make a system that is as rigid as a steel beam but as precise as a diamond, all while managing heat that would melt a standard processor. This requires a level of integration that has never been achieved at scale. The transition to wafer-scale, reticle-sized platforms faces significant scalability challenges because every single component must be perfect. One bad lens, one warped substrate, one imperfect thermal interface, and the entire system fails. The race is being won by the entity that masters the unsolved mechanical engineering challenges of cooling, alignment, and packaging. It is not about the speed of the photons, it is about the stability of the photons, it is about the stability of the path they travel. The company that figures out how to keep the light aligned while the machine heats up to extreme temperatures will secure the lead. They will be the ones shipping products that actually work in the real world. Everyone else will be stuck with impressive lab results that cannot survive the factory floor. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.